In many physics applications, you need to evaluate integrals where one or both of the bounds is infinite. These are called improper integrals, and they pose a challenge for numerical integration since it would take a computer an infinite amount of time to complete them. You might be able to get away with replacing the infinite bound with a very large number, but there's actually a cleaner and faster way to solve the problem. You just need to change three things about the improper integral: the variable, the measure, and the bounds. First, you need to transform the independent variable into a new variable. Usually, the reciprocal of the original independent variable will work, but there are fancier options. Second, you need to change the measure. This means changing the dx into a new dy along with some additional factors. This step requires a little differentiation. Finally, you need to change the bounds by applying the relationship between the original variable and the new variable. The integral changes form to have finite bounds which the computer can handle. In this code, which is available in a link in the description below, we're using the midpoint rule to evaluate the integral of e to the negative x squared from 1 to infinity. Here, we start y at its lower bound, corresponding to x equals infinity, and here we integrate until y reaches the inverse of x's lower bound. Here we implement the transformed integral, and the rest of the process follows the same as before. The answer we get is fairly accurate. Now, it's important to note that this code won't work if your lower bound for x is 0, because then you end up with an infinite upper bound for y. Instead, to handle integrals from 0 to infinity, we need to break up the integral at a cutoff point. The location of the cutoff point is up to our choosing. We evaluate the integral from 0 to the cutoff in the usual way, and then apply our inverse transformation to the integral from the cutoff to infinity. This code implements this split integral strategy by using two loops. The first loop evaluates the integral from x equals 0 to the cutoff point using our usual integration routine. The second loop evaluates the integral from the cutoff point to x equals infinity by using the transformation strategy. This code gives us a fairly accurate answer, but we can get an even better answer by pushing out the cutoff point to where the function has less curvature. This change shows that the cutoff point gives us a control over the accuracy of the code similar to the step size. You should now be able to use a computer to evaluate the improper integral of a given function. Use the codes in the links in the description below to evaluate the following integrals. Take note of how your choice of cutoff location affects the result. Next time, we'll take a look at one more method of integration that uses random number generation to evaluate difficult integrals.